Good morning, everyone. My name is Amitra. I'm from Group 7. Today, we'll be presenting about general trends and electronic spectra of actinoids. So, actinoids are radioactive elements and they form unstable isotopes. So, as the atomic number increases, the stability of the isotope decreases. That is why, actually, because of the stability decreases, your amount of your isotope, the elements formed will be in smaller amounts. Hence, this is why scientists actually find it harder to study the properties of this element. That's why they came up with a method called ion exchange separation method, which I'll further explain in the next slide. So actinoid series is actually formed by the insertion of electrons into your 5f orbitals. You can see here, starting from protactinium up to lawrencium, the electrons in the 5 orbital actually increases. But if you notice, in your actinium and thorium, there's no 5 orbitals. This is because in the electrons actually fill up the energy level which requires the lowest energy. For example, between 6d and 5f, electrons will actually fill up 6d because less energy is needed. That's why you see there's no electrons in your 5f. Next, in your early actinides, 5 orbitals are less core-like. Core-like means the electrons are actually closer to the nucleus. So less core-like, which means the 5 orbitals are actually further from the nucleus. So why are they less core-like? This is because there's a radial node. Radial node means there's a space where no electron exists, therefore they're further away. So that's why when there's a radial node, they'll be more penetrating. So when these 5 orbitals are more penetrating, they'll provide a better shield from the nuclear charge. So 5 orbitals and also 6d orbitals are actually similar in energy. That's why these d orbitals can actually contribute to your covalent contribution, and that's why you can form an oxidation state of above +4. But as your atomic number increases across the group, your radius will actually decrease. So that's why your 5 orbital will become more like a nucleus, and your 5 level actually become lower in energy compared to 6d. So electron will actually fill up 5 first, and this will actually, that's why you can only support up to oxidation state of +3. Beyond that, it cannot support. So next, in this table, you can see from thorium up to plutonium, these are the early actinides which behave more like the D block elements. They don't exhibit uniformity of the lanthanoids. But whereas the late actinides starting from americium, lawrencium, and also your actinium, all these will behave like your lanthanides, which is the 4f. So the difference between lanthanides and your actinides is that lanthanides is the insertion of electrons in 4f orbital, and the actinides is in the 5f orbital. Okay. And the ones bolded here is actually your principal oxidation state. The next method is called the ion exchange separation method. This method, like I stated just now, is to identify the properties of actinoids, right? So the stationary phase here would be your cation exchange chromatography, which is your negatively charged molecule. Eluent is your ammonium 2-hydroxyisobutyrate, which is your mobile phase. This is will help to carry your analyte, which is your molecule of interest, towards your stationary phase. So how to know which actinoids actually get eluted first will be the ones with the highest atomic number. As you can see here, highest one will be the 101 mendelevium. So that's why when this has the highest atomic number, it actually has the smallest radii. When you have a smaller radii, they will actually form a more strongly complex with the eluent. That's why you get eluted first. So next I'll be talking about the Frost diagram. Frost diagram is actually used to identify different oxidation state of element with different pH. So this one, in this table, is only for acidic pH. In your x-axis, you can see the oxidation number, and your y-axis is your energy, free energy. So the most important thing about Frost diagram is that the lowest point actually shows the most stable oxidation state here. So for example, I'll tell about thorium. The most stable oxidation state would be your +4. So this proportionation is actually a substance which undergoes simultaneous. They are the substance which undergoes simultaneously oxidation and reduction to form two products. How to know if you undergo this proportion is, this is called a convex curve and this is called a concave curve. So to know whether you undergo disproportionation, you have to see, for example, I give you an example, from 0 to +2 charge. This is the example which will undergo disproportionation because it has a convex curve, this part here, over here.
My name is Muhammad Nabil bin Sabtu 198770. Okay, I will continue my group presentation. Okay, I will explain what oxidation state for ethanol at +5 and +6. Okay, usually at +5 and +6 oxidation state, it occupy the linear or nearly linear oxidation unit state, which is ANO2 single charge, ANO2 2 plus single double charge. AN is actinoid and O is oxygen. Okay. Dominate the chemistry for oxidation numbers +5 and +6 of the early ethanoids: uranium, neptunium, plutonium, and americium. Uh, the ligands, when with this, occupy equatorial or near equatorial position. The linear of the actinide oxygen bond are very strong. Gas phase dissociation energies of actinide oxide are 618, 514, and 421 kilojoule mole, respectively for the uranium, neptunium, and plutonium. Okay, at this, oxygen atom exchange is extremely slow. For example, uranium O2 with double charge have half-life of 10 to the power of 9 seconds. Uh, dominance of the linear diacido unit. Okay. Dominance of this linear diacido unit at the actinoid. This proof that it is the covalent nature of the bonding that involve the 5F and 6D orbital. This property is completely different from the non-directional lysocytic bonding displayed by the lanthanide. Okay, this is the covalent bond between the 5F and 6D. Okay, the trans geometry, the example of the D sigma H, D infinity H symmetry. The trans geometry maximize sigma bonding by combining the oxygen 2p sigma orbital with an actinoid 6d. The symmetry and a hybrid formed by mixing 5f with the semicore 6p orbital of the which is U symmetry. This U and this G. The bonding does use both symmetric with G and antisymmetric U, O sigma SLC. For actinide oxygen of pi are bond are formed by combining the O2p pi orbital with 2,6d pi and 2,5 orbital of pi symmetry on the actinoid. Okay. That compared to the 4F of the lanthanide, the 5 orbital of the actinoid are more diffuse due to spectra of actinoid complex are more strongly affected by ligands. A convincing demonstration of the extension of 5 orbital into the bonding region is provided by the Iterus EPR spectrum of Pu plutonium 3 plus, which association 3 plus drop into CAF2. Each component of the hyperfine doublet that arise from the unpaired electron interacting with the 239 Pu plutonium nucleus is further split into 9 lines by neutron interaction with equivalent G is in the EPR spectrum. Internet contraction, large atomic and ironic ready because according the periodic table, when low go down the trend, it will go bigger. Example is radius of a actinide 3 plus ion is typically about 5 picometer larger than lanthanide 3 plus ion congener. It has actinide has high coordination number, like the larger lanthanide, hydrogen plus aqua ion are non-coordinate. Uranium in solid Cl4 is 8 coordinate. In solid EBR4 is 7 coordinate in a pentagonal bipyramidal array. Okay, that's all from me. Thank you.
Okay, hi. My name is Nakamra Tasha. Okay, next we move to electronic spectra of the actinide. Okay, the electronic spectra of the early actinide have contribution from ligand to metal charge transfer only within the 5f orbital to and 6d orbital and 5f to 5f transition. So the transition, as I said earlier, the transition between electronic state involving only at the f orbital and the 5f and 6 orbital, and this only happen to the ligand to metal charge transfer only. So as we compare the electronic spectra of actinide and lanthanide, for lanthanide, the F transition is more broader and more intense compared to actinide because in lanthanide, the F orbital interact more strongly with the ligand. So the molar observation coefficient lie between the range of 10 to 100 dm³ per cm. Okay, so next we move to this. As you can see, this is the graph of the fluorescent intensity versus the wavelength. So the ligand metal charge transfer result in intense yellow color of uranyl ion in the solution of a compound. So in the species such as uranium-3+, transition occur at the wave number between 400 to 300 nanometer, will give a solution of a deep orange red color. So it differs from neptunium and plutonium because in neptunium and plutonium, as the increasing effective nuclear charge, the separation between the 5f and 6d level will be increased too. So as the nuclear charge and the separation level increase, the corresponding transition move to the higher energy into the UV region of the spectrum, thus giving plutonium 3+ solution are violet and plutonium 3+ solution are light violet. So for this graph is about uranyl ion. There is a very strong fluorescent. It has a very strong fluorescent character with a strong emission in the 500 to 550 wavelength because it has the highest speed in here. Okay, so next is the example of metal in actinide. So there are several metals in actinide such as thorium, uranium, neptunium, plutonium, and americium. So for thorium has 8 coordination number, is the common, but it is common coordination number in thorium, but the common is simple thorium is a thorium 4 compound. For example, thorium oxide has the fluoride structure in which a thorium atom is surrounded by a cubic array of oxygen ion. Next, in thorium chloride 4 and thorium fluoride, the coordination number are also 8 with a dodecahedral and square antiprisium symmetry. So next for uranium, uranium has a more varied chemical properties compared to thorium because it has many oxidation states from uranium-3 to uranium-6. But the most common oxidation state in uranium is uranium-4 and uranium-6. This can be observed from force diagram. In force diagram, the uranium-3 aqua is the powerly reducing, and for uranium halide are known for the full range of oxidation state, which is from uranium-3 to uranium-6, which has a trend. If the coordination number is decreased, the oxidation number will be increased. So lastly is neptunium, plutonium, and americium. This element has a bit similar properties, but we can see from the force diagram to summarize their behavior. Neptunium dissolved in dilute acid to produce neptunium 3+, which is readily oxidized by air to produce neptunium 4+. Next, for plutonium, plutonium has a 4 common oxidation state of plutonium, which is plutonium 3, plutonium 4, plutonium 5, and plutonium 6. So, for americium, the most stable is americium 3+, because under strong oxidation condition, americium oxide and americium oxide 2 can be formed. Americium 5 disproportionate in acid solution. So that's all from us about actinide, and this is the reference that we use to produce our presentation. So thank you.